We're talking about resonance in tubes, right? What kind of tube is this? Open or closed? Closed tube, because it's closed at one end and open at the other end. And this has a natural frequency. You hear the natural frequency right there. So when the tube is that long, you get a frequency, which is that. Tell me the frequency formula. F is equal to V
over 4L.
V over 4L. For a closed tube, the first resonance is going to be V over 4L, where length is from here to here. Now what will happen when I pour water into the tube? The water, when it splashes at the bottom, creates a kind of a sound, right? And vibration. And that means you're going to hear the first resonance. But as water starts filling up, what happens to the length of the tube? Gets shorter and shorter. So the same vibrations now will set up resonance with a higher frequency. So V over 4L, L is going to go down. So as it starts filling up, the frequency that you're going to hear will be higher and higher and higher. In one way, without even looking at the filling up, you can understand that it is getting filled up by just listening to the frequency. So listen to the frequency when I turn this on. Is the pitch going up? See? It's higher and higher. It's going up, and you can feel that it is getting filled up. If you just imagine the beaker, measuring cylinder, is getting filled up. High pitch, high pitch. When it is too high, you know it's almost full.
What if it got so high that it shattered?
No, it's not good. See, it's high pitch, high, 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 almost. Yeah. So when it is like really on the top, the length is so small that it is the highest pitch. So the frequency that you hear depends on the pitch, depends on the length of the tube. So this tube right now has a frequency of its own, which is a natural frequency. This tuning fork has a frequency of its own, which is the natural frequency of this one, which is 384. If the frequencies match, it should resonate like this. When I hit this and keep it next to the mouth, do you see a little amplitude increase? Watch, hear the sound. Slight build up. Yeah, this is where I said, if you touch this one to the mouth of this, it can shatter this glass, right?
We should do that.
Do you have any old beakers you can show us?
Yeah.
Is it only if it's a higher frequency one?
What?
Because I have one of those tuning forks at home, and I put it on a glass screen protector and it didn't do anything.
What did you put on?
A glass screen protector.
Glass screen protector is not glass.
Definitely glass.
It's a perspex material.
Okay.
It's like plastic.
Well, my life is
Yeah. It's not real glass. So all those, what do you see on the screen here? That's not glass. Okay, so it's, in fact, what are you wearing right now? Is that glass?
The bank is the tuning fork.
Are you wearing glass? No, they are perspex. They are perspex. The material is perspex, which is why we wear perspex is because it's lighter and it has the same refractive index as glass. So lighter is very important because when you're wearing glasses, you don't want to carry something that's heavy. Yeah.
Is it less breakable?
It is unbreakable. Yeah, less breakable. Yes. It can break if you really want to break it, but otherwise it can take a lot. The only problem with that one is it can get scratches.
Yes.
Yeah.
That's the only disadvantage. Yeah, it won't break. It is light, but it will get scratches. Glass, on the other hand, will get less scratches, so it will be more clear most of the time. But if it drops, it breaks. That's the problem with the glass. So some people still prefer glass, even though it's heavy and all that, because it won't have scratches. Okay. Yeah. So right now, it is not in resonance. But if I fill this with water to some level, I can tune it to get it matched with this, and then you will hear the resonance. So what I'm doing right now is filling it up. Almost there. Almost there. Not quite. Better. Oh, wow. Okay. Well, I was right there. Should be almost there. Look at the resonance. You see the amplitude increase. So right now, looks like right. I think it's better now. Yeah, I think it's best. So this is 384. What's the frequency of this?
384.
384. That's why you're getting resonance. Now, knowing the frequency is 384, can we find out the speed of sound? Let's find out. What you need is the length, right?
Yeah.
The length of this water column, including the end correction. There's something called end correction. Including the end correction is.
That the little dip.
No, not the dip. The end correction is a correction that is above the tube. The antinode is not formed at the rim. It's formed at a height which is roughly 0.3 times the diameter of this tube. So the diameter of the tube is roughly 4.8 centimeters. So it should be 0.3 times that. What is 0.3 times 4.8? 1.44, 1.5 centimeters more than the rim. I'll tell you that number. So this one is 20.4. So 20.4 and 1.5 add up. 21.8. So that's the height. So we have V is equal to, frequency F is equal to V over 4L. And just because I matched up the frequencies, you know this is 384 Hertz, is V over 4 times, what is it, 21.8, right? Yeah. But in meters, it'll be 0.218. 21.8 becomes 0.218. So what is V equal to? That's the speed of sound at this temperature. How much is coming? V is 384 times 4 times 0.218, and that is?
It's 334.8.
3?
Yeah, 334.8.
3?
Yeah, 334.8.
334?
Yeah.
Yeah.
Did you multiply it all? 384 times 4 times 0.21?
Yep.
Yep.
It's supposed to be pretty hot in here.
No, it should be cold. 334 is supposed to be.
Is the water.
Maybe the water.
Is the water cold? Is the
That could be a reason also, yes. The water is cold, and so it's at 20 degrees Celsius supposed to be around 343. But of course, it's not 20 degrees Celsius here, it's kind of lower here. So the water is definitely cooler than that. So that is probably the reason why it is coming out this way. So, of course, it's a very rough method of doing it. Yeah.
Can you explain again the way we found the 1.5 centimeters and how you're measuring the length?
1.5 centimeter is called the end correction. The tube, you know, when you have a tube like that, the antinode is not formed here, but antinode is always formed a little distance above the tube. So it's like this. The antinode is formed above the tube, and that's called the end correction. The end correction is 0.3 times the diameter. So if you are taking a very narrow tube, then the end correction won't be too much. But this is a wide tube, so the end correction will be prominent here. So D is the diameter of the tube, which was 4.8 centimeters. So you calculated that one and you got that. The other reason that the answer probably is wrong is maybe this tuning fork is not as it is printed here. Let me check that and see. Because what is being printed may not be that's correct. It's perfect 384. Yeah. So yeah. So 335 meters per second for speed of sound at this temperature, because the water's temperature is low, and so this air is actually cooler, and that's why we get this answer. So you understand the concept of resonance, right? We can also see the resonance from here. When if I take the speaker right next to it and then change the frequency here. That is 200 hertz. That's 200 hertz. I'm going to increase it and see how the resonance comes in. 250-ish. 300. Getting close to resonance. 350. That point. That resonance. That is resonance. See?
He's shaking something over there.
Shaking something where?
Over there somewhere.
I don't know. What is shaking?
It's a ghost.
That is resonance. You can hear the amplitude increase. Now if I increase it further,
Maybe it's the moving blinds.
what's the sound?
It's not there anymore.
Hallucination.
No, it's
The second resonance, which is a first overtone, comes approximately 3 times the frequency. Now the frequency that you got is 384 hertz. So 3 times that is when you have the next resonance possibility. So what is 3 times?
11,252.
So let's go there. So I'm going to increase it to
Let's see if the blinds
Oh.
are shaking.
disconnect. So that is resonance. I'm going up. 600, 800, 10, 1000. Somewhere here. Amplitude increase, or here. That's right there. When you see a, it's annoying. When you see a higher amplitude increase, that is resonance here. Okay? So in closed tubes, you can have resonances. Same way you can have resonances in open tubes, and I'll show that right now.
He's good.
Maybe. I don't know, who knows what he has back there.
We can spin that one around.
What do you want to spin things around?
That's actually good.
So, now for this open tube, I'm trying to get the resonance again. Where is this focused? Okay. I'm increasing the frequency. That is resonance. That's your first resonance.
What frequency is that?
Around 200 and something. 250, 260. So next one should be around here. That one there. That's the second one. That's like the third one. It's tough to distinguish it because we are using just speakers. If we can actually calculate which frequency will actually create resonance on this one by checking the length. Let's check the length of this one. It's approximately 60 centimeters, but with the end correction of 1.5 each, so 63. So take it as 63 centimeters and find out what should be the resonance frequency for an open tube. For an open tube, it's going to be open on both ends. It's going to be open at both ends, and with the end correction of 1.5 centimeters on both sides, the fundamental is going to be like this. V over 2L. And I said the total length is 63 centimeters, including the end correction. So taking the speed of sound here as 340. What's the frequency? Frequency is 340 over 2 times 0.63.
270.
270 hertz, yeah. That's what actually you had the first resonance at. The first resonance came out almost there. So 270 will create resonance. So if I set up 270-ish, that is around 270, it should create resonance right there. That is resonance. You hear it, difference? That is definitely resonance. So 270 it is. So yeah, just understand the concept of resonance that way. Alright, let me give you one question after the other, and then we'll discuss about it. Listen to this question. A hiker determines the length of a lake by listening for the echo of her shout reflected by a cliff at the far end of the lake. She hears the echo 2 seconds after shouting. Estimate the length of the lake. This is a simple thing. So what it says here is there's a lake, there's a cliff at the end of the lake. She shouts and waits for the echo. 2 seconds after she gets the echo. So what is the length of the lake is the question. Yes,
What's the temperature outside?
20 degrees.
How convenient.
Yeah.
Can I take a guess?
Yes,
680 meters.
680,
343.
343.
It is, that's the answer.
Totally normal.
It is, that's the answer. That is the answer.
I'm talking about 640.
Because it takes 2 seconds for the sound to be heard by her. That means how long does it travel forward?
Oh, okay.
That was one.
343.
Yeah, it has to travel 1 second forward and then 1 second backward. The total time is 2 seconds for the sound to be heard. So 1 second and 1 second. So in 1 second it travels 343 meters. That should be the lake's distance, right, Garrett?
The mayor's tired.
Right, Garrett? Okay.
That's right.
Okay.
Yeah.
All right. Now,
What's it?
echo is basically the reflection of sound. Why am I not hearing the echo in this room?
Being disturbed.
Because
Hmm?
the door's open.
Yeah,
It's too fast.
There's a lot of objects in the way, I guess.
That is one factor.
'Cause you're not
If there are a
gonna-
lot of objects, then absorption of sound takes place. Like these materials are meant for absorption. So if you look into a theater, the walls are some material like this. The top is of that material because you don't want the sound to keep bouncing in and out. You want the sound to come straight to your ears and that's it. You don't want to hear a repeat of that. You understand? So if the walls of a theater are just concrete and the top is also concrete, it'll be awful to sit there and hear anything because it'll be like sounding back and back, back and forth. The sound is going to be bounced again and again. So you cannot hear the music or dialogues and all that properly if the theater is. That's what we are designing, right? When we design the theater, acoustics is a very important thing. You don't want like sound to be bounced back and forth. You want sound just heard once and that's it.
You guys designed the like Trinity Theater?
No, we are currently designing.
Yeah, the ACE Mentoring Club, every year they take up a project and design something or the other. And last year we designed a swimming pool for the school, which will take up the parking lot in front of our school, like the faculty parking lot.
So we're actually gonna get a swim pool?
We might. It depends on.
Where's the faculty gonna
I mean, it's not completely taken. The sides are still. We have parking on the sides. So every year we do this project sort of thing, and the Trinity actually takes the project up, and then if we get proper sponsors, last year we got that. 2 years back we did the Shamrock Grill. It's not called Shamrock Grill now because the donor is, I think, Derlas Experience, I think. So therefore, I think the name is something else, but it is a grill that was designed by the ACE Mentoring Club. They designed it, they estimated it, and all that we just presented to the school. The school was happy with that kind of a plan because school is the one who suggested that we like to get this done, but we need some planning. So the ACE did it, and therefore we got it planned up, and school got some sponsors to do it, and then they started constructing it. The same way last year with the swimming pool. It was a nicely built swimming pool, planned well. It's given to the school. If the school likes to take it, that's it. Now, year before last year, we did Veterans Memorial, which is still in the planning stages. School might construct it. Basically, the entrance of the school, that area will be modified. It's not a big construction. Yeah.
When would the pool be built?
I don't know.
Yeah, definitely not, but
It's a question of if right now.
I mean, right now there is no.
Still at it right now.
If the pool is built, the pool can be really, used for multi-purpose, not just for Trinity. We can, let others use it also and make a lot of money that way. Different schools will come to use it also. It's not just Trinity. So it will be a good revenue for the school. It may be expensive for initially, but later on it will be a good thing. Yeah,
Oh, so you all are working on the theater for this summer or what?
this summer. No, man. The ACE Mentoring Club prepares this project for the gala and presents it at University of Louisville. And then we take that plan and give it to the school and said, we did this already, and then now you can look into it and see if it is feasible, then go ahead and look for sponsors. So the current theater is a very old one.
So it wouldn't be finished by the next year?
No. It is just a plan. Right now it's just the planning stages. If the school is really happy with that construction, it may take a little extra space from both sides from the parking lots a little bit. But then if the school finds it really a good project, then they will look for sponsors. If sponsors also come up, then the theater will be built. So what we do in the ACE is just planning the whole thing, estimating as to how much it will cost to make this thing and so on, and then we'll present to school.
So they're like leveling the entire theater and building it from scratch.
Completely leveling it. Yes.
Would your
Oh,
plan for
really?
the theater give more leg room in the seats? Because that is an issue.
Really.
Maybe you
If
should
you want,
Is it?
It is.
if you
I don't
want
know.
that
You
to be
wanna understand.
inputted, you're gonna have to come to our meetings.
Alright. Come on, let's go to this one now. So, what is the minimum distance required for an echo to be heard? In this room, we cannot hear echo because the distance is too short. There must be a minimum distance for an echo to be heard. The reason is this, quiet. The reason is, if I hit two things together, if I hit, no. Did you hear it as two notes or one note?
Two. Two, I heard.
It sounds like two, or it sounds like one. It depends. Now, if I do this, of course you heard it two, clearly, right? What about this?
That was one.
Sounds like one. So when sounds come so close together, our ears cannot resolve it. That's called the persistence of hearing. Because you just heard the first sound, before that sound got registered by the brain, if another sound comes in, we get confused. But if the sounds come distinctly different like this, you heard two notes. That's because the time taken for the second one to come was more, the minimum, there was a minimum time required, space required. And the minimum time requirement is 0.1 seconds. So in 0.1 seconds, how far can sound travel?
34.3.
34.3 meters, that's right. 34 meters in short. So in 1/10 of a second, sound can travel 34 meters, which means what? 34 meters is the total distance for the sound to go and come back. So what's the minimum distance? 17 meters. So if you have a room where the distance is more than 17 meters, you will definitely hear echo. You understand that? So that's why longer, corridors or mountainous areas or big buildings nearby, they will create echoes. Because the distance is more than 17 meters, you clap, you'll hear the echo back again. Am I hearing the echo right now? I am hearing the echo right now, but I cannot distinguish it between the original sound and the reflected sound. You can't distinguish it. That's why we think it is just one sound. But we heard the echo.
Can someone yell in the lab?
Yeah, if someone is like far away, then if it bounces back and forth, then there is a chance that you hear it. Because 17 meters, it's not quite 17 also.
Let's prove it. Yeah, let's do it.
Yeah. So if you go to a big theater and all that, you definitely will hear echo. Especially in a theater, you won't be able to hear the echo because of the acoustics. Because they have absorbing material. So the sound that goes here, it will not bounce off at all. It gets absorbed. But the sound that hits a wall will get reflected because it is harder. You get it? So you understand this question? So whenever you are talking about an echo, remember that the echo is a reflected sound. It has to go and come back. Next question. What is the sound level of a sound whose intensity is 2 times 10 to the power negative 6 watt per meter square? What is the sound level of a sound whose intensity is 2 times 10 to the power negative 6 watt per meter square? So intensity is 2.0 times 10 to the power negative 6 watt per meter square. And the question is asking, what is the sound level? You know the formula for sound level? Sound level is 10 log intensity over intensity naught. So that's basically what it is. Log 2.0 times 10 to the power negative 6 over. What's it coming out to be? What's it coming out to be?
2 times 10 to the 6.
Yeah,
Wow.
but it's
63.
63 decibel.
Yeah, sorry.
That's what it is. So when the intensity is that much, it is 63 decibels. Next question. Here it is. A pipe in air at 20 degrees Celsius is designed to produce two successive harmonics at frequencies of 240 hertz and 280 hertz. These are two successive harmonics of the tube. These are two successive harmonics of the tube. If they are supposed to be the harmonics of the tube, the question is asking how long should the tube be? The pipe. And is it open or closed? So the question is asking, is it open or closed? And how long should the length be? Yes.
What are successive harmonics? Well, do like come one after the other?
One after the other.
Okay.
Successive harmonic means like you have one, the next one is the other.
Okay.
Yeah. Is it open or closed? And how much is the length of the tube?
Open.
Why open?
It is open.
Now it says it is successive. What are the harmonics of a closed tube? F1, 3F1,
3F1, 5F1.
5F1, 7F1. Remember the. Now, what are the harmonics of a open tube? F1, 2F1, 3F1, 4F1, 5F1, 6F1. So looking at these two numbers, one of them is one resonance and this is the next resonance. So which is,
It's 3/4. What's 3/4?
so if I take what is the lowest common multiple here?
2.
No, highest common factor,
40.
40. So how many 40s are this?
6.
6 40s. And how many 40s is this? 7 40s. So obviously this means 6F1 and that is 7F1.
I knew it was open.
So it is an open tube. So this is sounding the 6th resonance and that is sounding the 7th resonance, and that is, so once you know that 6F1 is 240, what is F1? 40. And what is F1 for an open tube? V over? So can you find L? When you know the speed of sound is 343, can you find L then? Easy. So 40 is equals to 343 divided by 2L. So L will be 343 over 80. How many meters?
4.3.
How much?
4.3.
Yeah. So the length of the tube must be 4.3 meters if it has to sound those resonances. One more question. Let's do it quickly. Well, there was one question for your homework. Remember that question: a stone is dropped from the top of a cliff and it splashes at the bottom and the sound was heard 3.5 seconds later. Did you manage to do it?
No.
No, I skipped that one.
Wait.
Magic.
I like the one about. I think I did that one.
See, this is what happens.
Let's do this.
The stone is dropped from there. Here goes the stone. And then it splashes and creates sound, and then the sound comes back. All this takes place in 3.5 seconds. And the question is asking for what is the height? So what you have to do here is understand this 3.5 second includes the time of fall and the time for the sound to travel. So if the time of fall is t, the time for sound to go back is 3.5 minus t. So what is the connection between h and t? Free fall. X is equal to VIT plus half AT square. So you get h is equal to half GT square, which means h is equal to 4.9 t square. Now what about this side? If it is going at a speed of 343 meters per second, for that much time, how far will it travel? That is, h is equal to 343 times 3.5 minus t. These two should equal out because they're both representing the same height. So what you do is 4.9 t squared is equal to 343 times 3.5 minus t. Now that becomes, if you can divide the whole equation with 343, what do you have? What is 4.9 over 343? It will be 0.014 something.
0.01428
28. 29 or 28?
9.
29. Is t squared is equal to 3.5 minus t. And then you switch that from side to side, you'll get this equation 0.01429 t squared plus t minus 3.5 equal to 0. If you solve that quadratic equation,
Well, I have a quadratic question.
you should be able to get this time
Hack mode.
as 3.34 seconds. I've got it in my head.
Did you actually? Yeah. Like, I don't
He's
believe, I
already
don't.
done
Now substitute that over here and you get h is equal to 4.9 times 3.34 squared.
4 or 5 digit numbers.
50.
You get 3.340 all time.
Yeah.
54.7.
So the height of fall is 54.7 meters. You get it?
I did it.
Say it again. But this,
No, I found.
yeah, you will get this equation if you use that method. But you'll only get the time t for going down, but this 3.5 is for the whole time. You have to set it up this way. There's no other way of doing it. You have to set it up like this. So if you have a car going like this, if you have a car at rest, sounding a certain frequency, and if you have another car from here moving this way with 15 meters per second and sounding the same frequency, this guy who is at rest, he is hearing beats. Now, why is he hearing beats? For beats, you need two frequencies. One is his own frequency, and the other is the frequency of that one coming to him. So f prime minus f is equal to, I think they said 5.5 hertz. And what is f prime using Doppler effect? It is v over v minus, yes, vs times f minus this f is equal to 5.5. You can solve for f from this equation because you know v is 343. You get it? Yeah, that is a problem that tells you about beat frequencies and Doppler effect. So sometimes you have to use Doppler effect in this manner. Suppose a car is running into a wall, not into a wall. If the car is heading to a cliff and sounding the horn, what happens to the sound? The driver hears the sound. One part of the sound goes and bounces from the cliff and comes back, as if another driver is coming to him. So again, you have to use Doppler effect concepts here.
Thank you.
Already.